Guess. What does that mean? What is meant by tripartite?
Color is in 3 colors.
Exactly. Very good. So a graph, very good. Tripartite means that the graph, the vertex of the graph can be colored in 3 colors, such that what? Such that between so that each edge is only joining endpoints with different colors. Is that okay? So for instance, let's say we have a graph like this. Okay, I don't know. Let's check. Okay, this graph is not bipartite. You can check it easily. This is not bipartite because if I color this is black, then this has to be in another color. Let's say white, but then we have white and white joining to each other. So in that case, how about we add one more color? So if we add one more color, this is so we add a new color. Does that work? Yeah, maybe. Okay. So if I'm coloring this graph using in this way, this is color white, this is color black, and this is color gray. Is that okay? Then between each pair of vertices, these two, they are receiving different colors, receiving different colors, receiving different colors, receiving different colors, and so on and so forth. Is that okay? Okay. Now, you may think of, okay, so this looks really like a bipartite problem, right? So you just can have one further choice of a third color. But then, so far, this is a very difficult problem. So we can have optimal running time to check if a graph is bipartite. But to check if a graph is tripartite, it takes exponential time so far. So far, the cleverest person in the whole world that we know, okay, cannot solve this problem quickly. It is still an open problem. To check if a graph is tripartite. So checking if a graph G is tripartite is a very hard problem. We call it a problem is an NP hard problem or NP complete problem. That's NP complete. So computer theorists has classified some problems into NP complete problem. So these kind of problems are very, very hard. So far nobody knows how to solve it in polynomial time, in n time, n square time, n cube time. These are polynomial running time. The only method to solve a graph, to solve this kind of NP complete problem at this moment is exponential running time algorithm. So it takes 2 to the power n or 1.5 to the power n time. So there's still no n square time, n cube time algorithm. So this is a problem that is, so it looks rather similar, right? Bipartite and tripartite, but just adding one more color will make the problem super hard. Okay, so this is what I want to tell. Now another concept. So another related concept. So we have talked about bipartite graph, and then just to add our understanding a little bit more, there are bipartite complete graph, okay, or complete bipartite graph, or whatever. Okay, so I should put it here. So complete bipartite graph. Okay, so what is the complete bipartite graph? So if you still recall, bipartite graph you can partition. You can separate the vertices into 2 groups. So maybe this is the left group, and this is the right group. Is that okay? Is that okay? Now, what is a complete bipartite graph? A complete graph is a graph that has edge between every pair of vertices. And a complete bipartite graph is you have edges between every left set and right set vertex. Okay, so this is a complete bipartite graph. And we call this so there are 4 vertices here, and there are 2 vertices here in this group. And we call it a K4 2 complete bipartite graph. Is that okay? K stands for complete. Is that okay? So I hope you still remember what is a K5. This is a complete graph with 5 vertices. So this is like this. So this is a K4. Is that okay? Sorry, this is a K42. K42 is having 2 parameters. So you have 4 vertices on one part, 2 vertices on the other part, and then you have connections between every pair of vertices here and there. Is that okay? Good. Okay. So next, let us talk about another concept called subgraph. So what is a subgraph? Subgraph. So let's say this is a graph G. And let's say there are labels on the vertices. Let's call it A, let's call it B, let's call it C, let's call it D, let's call it E. And then A joins to D. So this is the graph G. Is that okay? Let me get a graph H. And then let's say H is defined on the same vertex set as G. So we will have the same 5 vertices, A, B, C, D, E. So this is A, B, C, D, E. Is that okay? Let's join these 2. Okay. Now, we say that, okay, we say that H is, okay. Using set notation will be simple. So H will be something like what? H, let's say G is defined on the vertex set V and H set E. And then H is defined on the same vertex set as G. Let's call it V again. But it may have a different H set F. So we say H is a subgraph of G if what? If the edges that H can pick are always chosen from all the edges in G. Is that okay? So if H is like this, then we check every edge. This edge is joining A and D. This edge is joining A and D is also there. So this edge is inside the edge of G. This is also an edge in G because it is joining B, D. This is an edge. This is also an edge. So if every edge in this H appears in G, then we say it is a subgraph. Is that okay? Okay. Is this a subgraph? So if I change H like this, is it a subgraph? Yes. If I change H like this, is it a subgraph? No. Okay. So how about H with no edges? Is it a subgraph? Yes. Great. Because H set is empty. So this is very simple, right? Okay. And then make you more confused. So apart from subgraph, there is another concept called induced subgraph. So induced subgraph is okay. If you can remember, then remember. If you cannot, yeah, don't try to make this confuse you. So we have again G is V and E. Is that okay? We say H. This time H can be defined on a different set of vertices. Let's say U, and a different set of vertices F. Okay. Now, when will an induced subgraph happen? Okay, H. I don't have space. Maybe I use. Let me redraw it. Okay. Okay. So let's say G is a graph that is defined on the set V and E. Let's say H is another graph Now this time, let's look at the difference. So it need not be the same as V, U and F. So we say H is an induced subgraph of G if what? If the set of vertices that H is chosen from is a subset of the edges in G, and so you can pick vertices from G, but you don't need to take all. Okay, but then this is the strange condition. But then F is equal to E intercept. You don't. Okay, so we haven't talked about Cartesian product, but okay, so this is. Okay. F is equal to okay, this is better. F is equal to xy such that x, y are vertices in U, and this xy, the edge xy, is in E. Okay. Okay, then we use set notation. That's really easy. Okay. So what does that mean? Okay. So it's easy to have an example first. So let's call it the graph G. So we have vertices A, B, C, D, E, and let's draw some edges between them. Okay. So we may pick a couple of vertices. Let's only check A, C, E. Okay, A, C, E. Okay. So we can ignore some of the vertices in the original graph. But then we require that the edge, every edge in the original graph between the vertices that you are keeping must still be there. So if there is an edge AE, then you have to have AE. If there is an edge AC, you have to have the edge AC. And if there is no edge between EC, you should not have any edge between EC. Is that okay? Okay. So in this sense, this is called an induced subgraph. So why do we call it induced? Induced means that induced subgraph, you can think about this as for all the vertices that I don't like. So I like A, I like E, and then I like C. I like these three vertices. For all the vertices I don't like, I take it away. So I remove this B. So when I remove this B, I remove also the edge joining to B. I remove D because D I don't like. I also remove the edge joining with D. But all the remaining things has to be there. Okay. If this is the case, then we call it an induced subgraph. Okay. And then, so if this is the case, is it an induced subgraph? No, this is not. Is it a subgraph? Yes? No. Okay. A subgraph, you need to have D and B here. Is that okay? Very strange, okay? So subgraph has just the word subgraph, it is very, very relaxed. Okay, you don't care about the edges, but you care about the vertices. For induced subgraph, you don't care about the vertices, but you care about the edges. Okay, so this is the difference between these two. Okay? And now there's the last concept I want to talk about. Okay, this is called isomorphism, graph isomorphism. Okay, so let's say you have a graph G. Let's say V and E. And let's say you have another graph H. This time, let's say H is the U and F. Okay. Okay. Okay, so let me give you an example first. Okay, so we have a graph G. Let's say we have a graph H. So let's say this, let's call it A, B, C, the vertices here. And the graph H is called 1, 2, 3. Is that okay? Then if you look at these two graphs, you will say that, oh, they are very similar. They are alike, actually. They look similar, except of what? Except of the labeling of the vertices, right? So if I change the labeling of the vertices, let's say A to 1, B to 2, C to 3, then the two graphs will look exactly the same. Is that okay? So if this is the case, then we say these two graphs are isomorphic. Okay, iso means same, morphic means shape. So these two graphs has the same shape. Is that okay? Okay, so let's have another example. Okay, so let's try this one. Let me see. Let me see. Okay. So this is a graph. Is that okay? And this is another graph. So this is A, B, C, D. This is 1, 2, 3, 4. This is G, and then this is H. Are they isomorphic or not? Do they look alike? I am not saying about, so for a graph, two graphs are the same. It does not depend on its appearance when you draw it. It depends on the vertices and also whether there are edges between particular vertices. Is that okay? So for instance, even for this graph, I can draw it in a different way. And they are still the same graph. So I can draw it like I change A to here, C to here, B to here, and D to here. And then we have A, B, C, A joining to D, B joining to D. So this is also the same. If I change the labeling, ordering. So these two are still the same graph because they are still defined on the same set of vertices and they are defined on the same set of edges joining the vertices. Is that okay? Even I can also draw it in a different way. So I can draw it in like something like A, B, C, D. Let's say this is A, B, C, D. So I have this one. Is that okay? And then I can draw something like this. Okay. So this is still the same. So I still have A and C joining by an edge, and every pair of edges are joining two vertices. Is that okay? Good. So it doesn't depend on how we draw it. And now, this is my question. There's a G and there's an H. Are they isomorphic? And strangely, yes, they don't look the same, but there is isomorphic. If you change A to 1, B to 2, C to 3, D to 4, you can check that. Okay, between every pair of edge there is an edge. Every pair of vertices there is an edge. Here the same. Between every pair of vertices there is an edge. Actually, both of them are K4. Both of them are K4. And so they are actually having the same shape, isomorphic. Is that okay? Okay, so these two examples are extreme because we are looking at complete graph. Let me give you another example, maybe like this. Let's try with something like this. Let's try with so it looks like a lollipop. Yeah, it looks like something else. Okay. Yeah, but okay, so let's give it a name. This is A, B, C, D. This is 1, 2, 3, 4. Is that okay? Yeah, maybe I can actually call it a different way of names. Maybe I call it 1, 2, 3, 4. Is that okay? So I have two graphs. This is G and this is H. Is that okay? And then we can still ask the same question. Are they isomorphic? Are they? Yes, they are isomorphic. But this time, this is not just any random mapping. So in this case, we have to map A to 4. Is that okay? We have to map B to 3. Is that okay? But for C and D, you can change it. C can be mapped to 1, D can be mapped to 2. Or C can be mapped to 2, D can be mapped to 1. They're both fine. Okay. So if there exists a 1-to-1 correspondence, so here, this is the formal definition. So they are isomorphic, G and H. They are isomorphic if there exists a 1-1 correspondence between U and V, correspondence. So this is the bijection. There is a 1 correspondence between U and V. So let's call it F, such that F is going to map things from V to U. Such that what? Such that, how do we define? Such that what? Such that if you have some V1, V2 is an edge in E, then you must have if and only if F of V1, F of V2 is an edge in F. Is that okay? So this is the definition in mathematical notation. The meaning, you can capture it. So they are isomorphic if we can map the vertices 1 by 1. And whenever there is an edge here, there is a corresponding edge there. Is that okay? Then if this is true, then this is called isomorphic. If you are okay with this, could you please raise your hand? Okay. So we will look at some examples after. We will have a break soon, but we will look at some examples after that. But I also want to tell you about something about this problem. So whenever we define a new concept, we will ask, is it easy to check, okay, whether this is true or not true? I have a graph G, I have a graph H. Is it easy to check whether G and H are isomorphic? Now this problem, so far, nobody knows how to solve it quickly, very quickly. But still, we can solve it in exponential time. But so far, okay. But so far, this problem is a very strange problem. Some people believe that it is easy. Some people believe that it is hard. But nobody can show that it is really easy or it is really hard. Now, what is meant by to show that it is really easy or show that it is really hard? To show that it is really easy, it means that we can give a polynomial time algorithm. Let's say it runs in n squared time, n cubed time, or whatever. So nobody knows how to solve it in that quick time. On the other hand, this problem is also not very hard. Nobody knows whether it's very hard. If a problem is very hard, usually we'll check whether it is an NP-complete problem. So NP-complete problem is some kind of a standard to say that a problem is really hard. Okay, nobody is able to show that it is NP-complete. So there is a question whether this is a hard problem or it is an easy problem. But in contrast, we can define another problem called subgraph isomorphism. What is subgraph isomorphism? Subgraph isomorphism is subgraph isomorphism is like this. We have a graph G and we have a smaller graph H. Is it able to find H inside G? So it is not exactly a 1-to-1 correspondence between the vertices here because G is much larger, H is much smaller. Is that okay? Do you understand my point? Okay, and then G is much smaller and then H is much smaller. G is much larger. So you don't have a one-to-one correspondence between the vertices. So that means that sometimes some of the vertices here may not be relevant to H because we may just remove it. But after removing those vertices, is it possible to remove a certain number of vertices here such that the remaining graph is isomorphic to H? Now this problem is known to be hard. This is an NP-complete problem. Okay, NP-complete is hard because nobody knows how to solve it. Okay, it may not be really hard. It may be easy, but still at this point nobody knows how to solve it. Okay, but yet, okay, most people believe that it is hard. Okay, so a subgraph isomorphism problem is a hard problem, but if I change it a little bit, if I have H and G known to be of the same size, if G and H are known to be of the same size, then this becomes the original isomorphism problem, and it is not known to be easy or hard. So this is what I want to convey to you. Okay, if you are interested in knowing more about hard problems, check for this word, NP hardness. Or what? Yes. Or you may check for the word called intractable problems from the internet. Intractable. So intractable means you don't have efficient, you cannot easily solve it. Okay? Okay, so let's take a break. And after the break, we will have some examples of this graph isomorphism. Okay, let's take a break.